So today I want to talk about trigonometry. And in particular, I want to give the basic geometric intuition and motivation for the definition of the three most common trigonometric ratios. So all the geometric intuition starts with right angle triangles. So here I have a right angle triangle. I'll label the side lengths A, B, and C. And in trigonometry, I want to focus on one of the particular angles, not the right angle, one of the other two, so I'll pick this one. And I'll label it as well. This is lowercase Greek theta. Now from the perspective of this angle, I can also name these sides with more familiar names from trigonometry. This one here is called the adjacent side. This one's called the opposite side. And this one, as always in a right angle triangle, is called the hypotenuse, the longest side in a right angle triangle. So from the perspective of this angle theta, this is the opposite side, this is the adjacent side, and this is the hypotenuse. And the idea in trigonometry is to look at ratios of these sides. In particular, the sine is going to be asking us to look at the ratio of the opposite side over the hypotenuse. The second core trigonometric ratio, cosine, is going to be asking us to look at adjacent over hypotenuse. And finally, the third of the three most common trigonometric ratios, tangent, that's going to be asking us to look at the ratio of the opposite side to the adjacent side. What do I mean by this? The idea is that the angle theta is determining these ratios. Right? So we can write it like a function. I write sine of theta, and I look at this picture, and I know that sine is supposed to be opposite over hypotenuse. So sine of theta in this picture is going to be b divided by c. And cosine of theta is going to be a divided by c, adjacent over hypotenuse. And finally, tangent of theta is going to be b divided by a, opposite over adjacent. So the idea is that just from theta, I should be able to get this ratio. Now, how does that make sense? This is not something I'm going to prove. I'll do that in another video. But I'm going to give you the intuition for why we're looking at ratios and why it makes sense to look at ratios. So first, let's see why it doesn't make sense to just look at lengths. Okay? If we're just looking at lengths, then I can take a picture like this. This is also a right angle triangle. And let's suppose that I've drawn it so that this angle is still theta. Right? It's just that the triangle itself is smaller, but I kept the angle here, theta, the same. So now it's clear that just by knowing theta and the fact that it's a right angle triangle, I have no idea how long the opposite side is. It might be this long, it might be longer. I could draw an even bigger triangle and make it longer. So knowing theta doesn't tell me how long the opposite side is, right? But the idea of the ratio is to say, knowing theta does tell me how long the opposite side is relative to how long the hypotenuse is. That's the sine ratio. Or how long the opposite side is relative to how long the adjacent side is. That's the that's the tangent ratio. So let's see that in action. Let me draw a picture of a triangle of side length 1, right angle triangle. The side length is also 1. A simple application of the Pythagorean theorem would tell me that this side length is the square root of 2. And because of the symmetry of the triangle here, this must be 45 degrees. Now, if this is the picture I'm using, what I get is the sine of 45 degrees is equal to opposite over hypotenuse, 1 over the square root of 2. And the cosine of 45 degrees is equal to adjacent over hypotenuse, also equal to 1 over the square root of 2. And the tangent of 45 degrees is equal to opposite over adjacent, 1 over 1. So just 1. Now these three ratios were calculated with this particular picture that I drew. But the idea behind trigonometry is that it doesn't really matter how big or small I draw the triangle. As long as I'm looking at ratios, those are going to be constant, right, for a given angle. So in particular, if I draw a much larger triangle, right angle, which is also a 45-degree angle here, which I can arrange by, say, making this length equal to 2.7 and this length equal to 2.7, right? And the idea is that, well, first of all, the tangent of 45 degrees, which is equal to the opposite over the adjacent, 2.7 divided by 2.7 equals 1. In other words, the ratio of these two sides, because this is still a 45-degree angle, the ratio of these two sides stays the same. And also the ratio of this side to this side, let's label this side C. We could solve for C using the Pythagorean theorem if we wanted to, but the idea is that the sine of 45 degrees based on this picture is equal to 2.7 divided by C, opposite over hypotenuse. But based on this picture, we already know what sine is. We know that the sine of 45 degrees is equal to 1 divided by the square root of 2. I'll write that a little bit neater. And that tells me, these two things together tell me that 1 divided by the square root of 2 must be equal to 2.7 divided by C. So C must be equal to 2.7 times the square root of 2. And this just follows by the underlying geometric assumption of trigonometry, which is something that can be proved, although I'm not proving it in this video, I'll prove it in another video. But the underlying assumption here is that since this is 45 degrees and this is 45 degrees, this ratio, 1 to root 2, is the same as this ratio, 2.7 to C, whatever C is. So the ratio of the lengths of the sides of a right angle triangle is entirely determined by this angle here. And that's the basic idea behind trigonometry and the basic definitions of the three most common trigonometric ratios.